here. Hi everyone, and we're back. Let's do this. So, not gonna do too many notes today. Not gonna talk a lot today because it's a busy Monday, and we've got work going on with other things. And I'm actually in the middle of like a very kind of like an intensive debug session right now. So my head is quite in Zephyr at the moment and very custom Zephyr, so that's kind of bugging me. But I did say I'm gonna do this, and I will stick to that. So what happened is I went and showed someone at work my CPU, someone who's worked on Verilog for quite a while, or rather someone who's done. Verilog isn't the main point here. Someone who's done digital design for hardware for quite a while, and they told me that the CPU design was quite nice, which was quite like, that's really encouraging. That's really promising because then at least I'm on the right path. But then they told me as my CPU grows and as it becomes more complicated. I don't know. I haven't told the Discord people. Live again. Live again. Obviously, if you're joining now, and you can see the description in the video will have like a link to our community, and you can jump on there and see what you want, or rather join us and talk to us. But so I was talking to someone at work, and they told me the more complicated the design gets, the more it'll start. The debugging for the design is going to start getting very hairy, because then we're going to get to a point where you won't know what is failing, and then you'll have a lot of like very low code, and it just basically is going to be a problem. So what I was advised is to build like a little try and build a test bench, and someone sort of like mocked up some code for me that I've been reading all night and trying to understand. I still can't get it, but I'm gonna write it. I usually understand things when I write them, and that's gonna be really helpful. So I'm just gonna try and write it out, and if we manage to understand all of it and write all of it out, then probably at the end of the stream I'll try and run it and see what happens. I'm very doubtful it's gonna work because I expect it's gonna break a bit, and I haven't spent enough time on this, but we'll see. So let's make a thing. I think the thing I can do is probably go like, just think a bit. I'm gonna think a bit. I need to make a new file. It's stubs.v. We're gonna need to, let's save it, and then actually let's split. I think I can do this. Split. So we're gonna and then in here we're going to open main.v so that we can sort of follow what's happening there. But the first part that we're gonna need to do is we're going to need to stub out this the silicon blue high frequency oscillator, and also the silicon blue RGBA driver. The reason for that is because the RGBA, these drivers are known only to Lattice or Lattice. I don't know how you say the name of the company. I've never had someone who knows how to say it, so I don't know. But I've only seen it written. I should ask it what. So basically, the silicon blue modules or the silicon blue primitives are not known by iVerilator, and iVerilator is what we're going to use to run the tests. So what we need to do, number one, is to stub out this iVerilator modules so that they so that the tests can know what to do with them. And also, if we do not step out the iVerilator modules, um, then the problem is going to be that in our tests, the we won't have a clock, and our whole CPU is tied to this clock, over here. So the first thing we need to do here is just basically build some stubs for the two silicon blue primitives, and then we'll go forward and then write the test bench for it, and then let's see how that works. So I'll try and do this properly, and I think this is I'm in stubs here, so I'm gonna do some module. No. Let me on a go all the way to here. Yep. So here I'm gonna do module SB HF OSC, and this one will be it will have the clock power enable high frequency oscillator and the wire out. So this will just have those things, and then we can use that. So input HF. This is actually quite cool. CLK HF PU. I'll keep stopping for questions every now and then. And then input CLK. This is actually HFEN. I see now why they told me this is gonna happen. And then we're gonna have, I think, output CLK HF. What I've been made to do here is I am now actually consuming my own interface. So in some sort of weird way, I'm learning how to write very real Verilog. If that makes any sense to anyone, I'm learning how to write very real Verilog, because this is now going to force me to consume it's like I become a user of my Verilog rather than the writer. And if my experience from software tells me anything, it's that whenever you if you design a library for people who do interfaces to use, and you actually try and write tests for that library, you start realizing how good or unintuitive or intuitive it is to use, and that makes things very normal, basically. So here, what we're going to do, I think that I need to finish this, and I think this is just the oscillation for the clock. So let's say 100 megahertz clock, 100 megahertz clock. It doesn't really, do we really need to know module? I knew there was a problem somewhere there. Something is wrong. No, this should not be like this. Is that the problem? No, input clock. Okay. Let's go here. Pull in a window. Writing Verilog test benches. This is stubs for silicon blue in Verilog. Verilog. Seriously, why would you write a manual and then like it's not available? I see. Thank you. Thanks. But still, that doesn't fix it. Thank you. Thank you, though. This still doesn't fix it because I should have a valid module in here, unless I'm seeing stuff. Unless let's try and find the thing that makes this break. It's not. It's none of this. It's none of this. It's none of this. And if I go down here, that's the same thing we're doing. Output, output, output. Should we name this? Input CLK. CLK. Can we just name them and see? CLK and in, and then CLK out. Oh my god, I don't know how to write this. Somehow I've managed to already mess myself up. Yeah. Device and the test. That's fine. Module. No. Okay, cool. So that's the time scale divider. I know where to put that. That's in the other place. But my module is not like, it just starts as a module and then it just doesn't work out. It just dies. Why? Why? Yeah. Well, okay, cool. So how do I do this? How do I do this? Really simple one. I don't see any questions, so I might not be able to answer questions. You guys might need to help me. Module design, that's it. That's really it. Output Y. But yeah, module T. Is it because I need? No, that's actually no. That's not my biggest issue. My biggest issue is stopping lattice SB primitives. Yeah, I understand what it does, but are you doing it in a test? It's not too complicated. I can do what it does, but okay. Who's here? Who's here? They can help me. Who's seen this before? I see two of you here, so I don't know who's here. Yeah, but this is how you're using them. This is how you're actually using them, and that doesn't actually matter because the way I'm using them actually works. It's here. It works. Okay, that's fine. It's when I'm stabbing them. If I just take off everything. Wait, did you see that? Did you see that? Did you see that? Did you see that? Okay, let's do this. And you see, it becomes an actual thing. But if I add another one, CLKHFPU, yes, CLKHFEN. If I add another one, it dies. Do you want me to do this? I've seen that somewhere. Okay, cool. We're getting somewhere. We figured something out. We figured something out. That's fine. Let me see. Out. Okay, cool. So if I do this, you like it? And if I say out, okay, this is a big problem. Writing stabs for lattice silicon blue primitives. No, that's not actually what I want. That is not actually what I want. Using SB primitives in Appio test benches. Yeah, Tiny FPGA is actually used. It's actually from lattice, so we should be able to do. Yeah, please. This is exactly kind of what I need. Yeah, this is just a normal one. This is fine. This one is cool. This is a normal test bench where you have a time scale and then you just do. See that? No, I don't know. I don't know. I don't know. What? Because look, let me just show you. C dot ls cd. Which one was the first one I did? One ankit less. Does this have a no cd dot eco ice. No. CD led RTL. Okay. No. Let's RTL. LS. Yeah, you see? And then if I go here, up here, assume if I go here, I'll show you what we're trying to do. So if I go here, there's this command that basically up here simulates. Up here sim, and then we just take the test bench main t dot v. This will make yeah, you see, it's simulating our, this is a device, this is our test bench, and this is our device and the test, and then this is signals. So the signals, and then it's changing all of them. That's what it's doing. Yeah. However, this is code I did not write because this is just code from Sean Hyman's videos. So let's actually look, but this one won't actually be for the thing itself is quite easy because you just put some inputs into your Verilog, and then you watch for outputs. That's what that bar is doing. This part is like super simple, and I can kind of walk you through it quite easily. So here we basically make the top module, and then we construct a device and a test. That's what DUT means. And then we feed this input into the module, and then we run like a clock. I guess this module is using some sort of clock, and then it's flipping on those. And then again, initial begin. We know this is setting the defaults at the beginning, and then after the initial begin, we run this stuff. You know, something is popping. Is my phone too close? Is it my watch? What would be popping? Is it a loud pop? That's not cool. I wonder if it's my phone and the radio too close to the microphone. Okay, so as you can see, this code actually is quite fine and it's quite easy. So we basically run the code and we run a clock, and then during the clock we assert on what we expect, and then if we get an error, we run an error. That's easy. That in itself is easy. When we're writing this one line at a time, it's easy to consume. The problem is, let's look at this. The problem is that this code expects some sort of input, and then based on that input it does stuff. You see, it doesn't use any primitives from lattice. So this is quite easy to simulate because you give it the clock and then you kind of simulate from there. Bartholomew, is the audio better now? Let me know, or anyone else who's on the stream, let me know if the audio is better. So this code is quite easy to simulate, as opposed to our code here, which actually uses this. Our code here uses this silicon blue primitive. This one. The silicon blue primitive is primitive from lattice. Appio uses iVerilator. iVerilator for testing. iVerilator. Excuse me. I'm not a robot. I just Google this stuff enough. So Appio uses iVerilator, and this does not know of the Silicon Blue primitives. It doesn't know about them. Oh, I know this website. It does not know this. It doesn't know. It does not know um, about the primitives from. It's almost like we are doing a test. Assume you're writing test-driven development for some software, and then inside your software somewhere you have some API calls to some external API that you don't control. So what you usually do is you can it, or you stub it, or you mock it, or you fake it, whatever name you want to do. So what we're actually trying to do is learn how to stub or mock or fake some external API from some external API in our Verilog in hardware design. So there's these primitives that we have that we're using that we're trying to mock out, and that's the problem. That's our problem. Mocking silicon SB primitives in Verilog. No, we've already done that. This is fine. The test bench itself is quite easy, and I assume this is why the it's actually, I'll be honest, our CEO at work is the one who's advising me on how to write this stuff, and he's been doing this like since the 70s or something. Oh, hardware design, digital design. I don't think FPGAs were FPGAs are quite new, but he's been doing this for long, so he's really good at it, and he's trying to teach me how to do it. So, and I assume this is part of the challenge. Go and learn how to do this and figure it out. So I am trying to figure it out. I'm trying to figure it out. And you guys are coming along the journey with me. Let me see. I hope my audio is better. I'm really sorry if it's like really bad. I'm quite sorry about that. User's guide, finding and binding, mocking, stubs, stub. I'm kind of sure it's not gonna work because this should just, if I write normal Verilog in here, it should just work. Look at this. Look at this. And it already doesn't work. So there's something I'm doing wrong. So module, TB, no, star, I see. It's because this is not the normal one. So if I, okay, let's do TB, tiny CPU, tiny CPU. So this is a test bench. This is how we're going to actually do it. And then in here we can do something like wire, lead, red, lead, blue, lead green, green. And that should enable us to have all the wires, and then we can have tiny CPU, DUT, something like that, and then we can go on. This would work, but that's not what we're doing right now. We need to stub out the stuff. Anyways, perhaps I just type it all, and then we build it up, and then we just let it give us an error, and then we see. So module SB HF, that two spaces, SB HF OSC, and then in here I think in here I want to do input, and then input is CLK HFPU, okay, and then input CLK FPU, FPN. Okay, cool. And then output CLKHF, and that's it. And we can do that, and then we can do that, and then this should work. I will leave it at that. I will leave it like it will work like that. Reg, and then I can come here and do reg CLK. Remember, a register is something that stores. A register stores 1 bit of data. Its default is 1 bit of data unless you give it like unless you give it some sort of range. Okay, CLK. Let's do that, and then assign always. What does the cheat code do? What does the cheat code mean? Document. Sorry about that. I had to deal with the fire in the other room. Okay, cool. So let's keep doing this. Let us discover how hard it is to do this and why people became so rich doing this. Okay, so let's do that. Always. Wait, we were looking for the cheat sheet. I think it's in Lattice. No, HDL maybe. Verilog reference, and I think Control F always. What is it? Let's see. No, that's not the one you're looking for. Always begin. I don't see. Fine. This is something new. Verilog always. Okay, so it just executes this sequentially. So this basically says it's gonna be always 5, and then CLK equals CLK. So this apparently gives us 100 MHz simulation of a clock. Okay, and then let's do end module. This is the part that worries me. That the thing is not going like, oh, you wrote actual Verilog. It's not going like that, and that's a problem for me because that means it won't work. Let's actually try and build it. If I recall correctly, I have some notes over here. And then in here, the other thing we need to do now is it's not just the silicon blue. We need to mock. We also need to mock the RGB driver. This part is the easy part. This part, it's either the easy part or the hard part. So much. Let's go here. It's just tabs. Like literally, this is just tabs. So here we need to do module SB RGBA ERV, and then in here we need to go and actually make all those input RGB LED input RGB RGB 0 PWM input RGB 1 PWM input RGB 2 PWM. I'll stop for questions just now. Input current, and then I think these ones are outputs. Yeah, it should be output. Output RGB 0. Output RGB 1. Output RGB 2. We're just gonna pretend like things work, and then after they don't work, we'll fix it. Okay? It's good. That's my feeling is because my editor is saying this is not Verilog. My feeling is there's something I'm missing that will not work here. Equals RGB PWM assign RGB 1 equals RGB 1 PWM, and the part I'm doing is this one in case someone wants to notice this 3 is what I'm doing. I'm literally copying it over. I just following some RGB 2. I'm making everything it's hard to do something new while everyone watches. And module. No. Just like that. Okay. So this builds a test bench. No, this is not a test bench. This is a start file, but it's gonna explode at some point. But we will get to it exploding, and I do not like. You see this module should be highlighted, and it's not. Anyways, let's go to the end and see if the let's go to the end. Let's see first. That's okay, and see if it actually is that how you write them? Is that how you write them? Main td.v. So we just want to call it main main testbench.v. Okay, and then in here, what we actually want to do is now actually do the testing of the code, which I think is going to fail again. So here we want to do time scale, and then we want to go like 1 ns, I think, of 1 ps. Yeah, and time scale, if I recall correctly, is just it's really what it sounds like. Yeah, here's it. It's like time scale specifies time unit precision. So we say what unit it is. It really says make this. Let's run at let us run at microseconds. Let us run at nanoseconds, and then the precision is like I think per second or something. I don't know. Let me look at questions. Any questions so far? No one's here. That's cool. That's chill. Let's quickly do this. So what is gonna happen here? Once we divide the time scale, we need to start doing the stuff that is happening here. What's the first thing we need to do? We need to make a module, and then inside the module we need to make some outputs that we can observe, I think, and then we can go from there. So module CPU TB, or is it, no, it's the opposite way. TB tiny CPU, TestBench tiny CPU, and then I believe this doesn't have a module. Does it? Module. And another problem, because this doesn't seem to be valid to Verilog. And this is a problem. This is an issue. So this doesn't seem to be valid Verilog as well. Okay. No, there's no space. There's no space. So it's fine. So let's just keep. Oh. It was working. It was working on this one. I just doubted myself. And my machine needs me. My NeoVim, somehow my NeoVim doesn't get anyways, wire. Let's define these outputs. Lead red, lead blue, and then lead green. So that should give us the wires that we're going to be using in here. And then I want to do tiny CPU device under test. So this defines oh wait. Okay, DUT. But it can be DUT as well. Under test. Under. Verilog DUT. Yeah, unit of test. I see. So you have a device under test, which is the whole thing, and then you have a unit under test, which is like your device under test, integration test, unit under test, unit test. That's how I'm going to understand them, and you can't convince me otherwise. So tiny CPU, and then in here we want to do dot lead red, dot lead blue, dot lead green. I immediately know this syntax. Wow, see. Thank you. Lead red, lead blue, lead green. So the ones above, and then that fixes that, and then you can do that, and you can do that, and then you can do that, and then you can do that. And the thing I just noticed is this. Look at that. What we're doing, yeah, this is cool. What we're doing is we're learning how to write Verilog APIs. So look at this, SP, the data type, the name of the thing, and then look at how we're doing it. You see, we put one binary one here, and then we put a register in here, or a wire. Wire and register is kind of the same thing. I'm still confused. We put a wire in here. Look at what we're doing here. We made dot red, dot dit, and then we add their values in there. See, so basically what we're learning how to do by writing test benches, what we're learning how to do is actually we are learning how to write Verilog APIs. So we're probably learning how to write write IPs that are going to be used by code that is not written by us. Rather, we're exposing it so that other people or other developers can do this. Okay, so dump waves for GTK. We'll get to GTK later. GTK is this. GTK is this. Appio sim. What did we say? Appio sim. Appio sim. Yeah, Appio sim main tb.v. This is Appio sim. So this, look, this program is GTK wave that sees this, basically. So if you dump the waves out, GTK waves knows how to use them. Cool. So here, what we want to, you see here, they dump these, they dump them for GTK wave, so that's fine. And that's kind of what we want to do here. So what we want to do here is how did that work? Initial begin. So the first thing we do end, and then here what we want to do, I think we have some primitives we can use from Silicon itself, and it's something like dump file, and then it's dump file. Tiny CPU TB, I think. .vcd. Oh wow, I see now. Let's see. I see now. So GTKW. This is GTKW, but you can use VCD. So this file probably comes from the dump. Let's see. Appio sim. Okay, cool. I'm still highly doubtful that I think that our thing will work, but it's fine. And then here I want to do dump vars. That's tiny CPU. So like push out all the This is TB. Yeah, I see TB. Tiny CPU, and then that's that, and then what I want here is 0, and that should have a comma in it so that we have the thing. And I think that's that, and that should give us the first waves for GTK, I think. Let me look at the other thing. Dump var 0 test bench. Yeah, that's what I did. Dump var 0 test bench. So this module here, this module is here. If you look at here, dump var 0 test bench, and this is module test bench. Cool. So that's actually what I did. Okay, now the next thing we need to do is run a simulation. Inside here, so I saw two bodies of code. Inside here, they run it in here. So what I can't do is I can actually do another initial begin, and then I can run my test code in there because I think it'll look simpler and then it's easier for me to understand. So initial. I usually try and write code as simple and as straight. I repeat it or I write it straightforward enough that I can understand it, and then later I can remove the repetitions, because if you just write it the first time, just like straight up, it becomes quite difficult. Wait a bit before running, and then let's do hash 200 cycles. I think that should be okay. And then the next thing is, I think I just want to check the RGBs. I don't want to start. Look, our CPU is quite complicated, and that's why it's open. So there's quite a lot of stuff we can check. We can check that these registers are being handled correctly. We can check that this instructions are run nice. We can check that these ones are run also nice. that means actually writing very complicated tests, and I don't think I know how to do that. So the first thing I really want to write a test for is just to check, does my CPU, which is the same thing we do when we look at the thing, does my CPU actually go out and light the three LEDs? That's what I want to check. And then once I kind of build an intuition for that, then we can start writing more complicated tests. Okay. Let me see for questions. No questions. Yeah, I don't know. This must be either a very boring or very exciting. So if unit, if unit under test R0, so here we start doing this part. See this? We're using R0 here. Okay. So if unit, so the first thing we're testing here is this. R0 should always be 0. You see? So let's test that. Let's test that. Unit under test R0 is not equal to 32 binary 0. Okay? And then if that's not the case, okay? If that's not the case, then let's do a display. Display takes in trying to remember. Display takes in a message. Fail something like R0 expected to be 0, something like that. But you can add I think that we got, this is the nice one, got, yeah, something like that. I think that should work. Got 0, so something like that should work. And then we can do ut. This is the part that I like about Verilog, ut.r0. It's sort of like C. Test R0. I think if I remember right in my notes. Okay. Cool. So now that's a simple one. I wanted to do that one because that's a register one that's actually handled. And then let's do we can actually add an else here, which is kind of weird for me because I guess that's because the display is in the body. That's because the display is in the body. Yeah, else display. Okay. Else display I think pass something like that, because we are writing our tests ourselves, so we actually this test framework does not expect you to doesn't have what do you call it? You know, test frameworks can make a 0 or a 1 for you. This one doesn't, so it's kind of like stuff. Okay, let's go R1. Where do we use R1? You see here, we use R1, yeah? Use R1. Can we test anything? R1. So if we pass in something to R1, yeah, let's test the in command. So, test. So this is what we're gonna do. We're gonna put R1 in the program counter, and then do an increment on it, and we should expect that it has been increased. Okay. Yeah. Let's try again based on the stuff that we just wrote. If yes, let's see ut dot r into 1 is do 32 B1, and then that's that. And then we have to do a display, the normal one, fail, R1 expected, R1 expected to be expected 1, because we set it to 0. And then in here we'll do got 0B, and then out, and then UUT dot R1. I'm wondering, so okay, also else display class R1 is equals to 1. So yeah, something like that. It's so odd to it's so odd to use the assignment operator as the equality check operator. It's so odd. That's a bit like unnerving. I have a meeting in like half an hour, I think. So I'll have to dash soon, but this is okay. Let's actually persist. Let's persist. What are we gonna test next? We didn't give it any instructions, but all our instructions are just increments. So for now it's fine. If UT, let's check R2. Actually, we don't actually even have to write that. I think we're gonna skip that for now. Why not? Let's just finish, and do that. And then after we do that, we do that. And then now let's actually do a monitor on the. We did some initial. We actually tested our instruction set. Initial, begin, and then here we want to do monitor. So monitor is just like a sat in some weird way, because it looks at some wires. It basically looks at wires, and then based on if those wires are. So let's print out the time. That's cool. That's actually cool. It's cool that I can remember that. And then we can do LED, and then here we can do RGB. Cool. And then after that we can do I think if I recall correctly it was BBB, because it's a bytes. Because it's a bytes, so it'll give us like 0001111, something like that. And then we can do something like passing time. That's the first thing that we give. We printed a time, and then we need to pass in the 3 wires: red, green, and then lead, blue, I think. And then this is end, and then end. I highly doubt this is gonna work. But let's see. You see here we did what were we running here? Appears main.tbb ls appears like I said, I thought this would not work. Stubs V22. And Vimp stubs number 22. Buffalo's coming. At least, yeah. At least we can remove that. So, stubs, that has been declared. Error module already declared. Da, 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 da. V stubs meh dot meh ls. I think it still fails. Let green. No, let green. Let green. Let green. I will avoid doing that. Wait, our test ran and they failed. I know why they failed. They failed because we're not stubbing the clock. And if we stub the clock, we get the other error, which is the modules have been defined. So, just as I expected, it's something I do not know how to use this, and I need to learn a lot more. It's probably going to be a 5-minute thing that I'm going to ask the people at work and they'll show it to me. But as of the moment, this is a bit difficult for me right now. And I'm going into it's 20 minutes to my meeting, so I need to go into my meeting and then we'll see it. Anyways, thank you so much. Thank you so much for everyone that showed up. Thank you so much for showing up and being with me and watching me learn code and stuff. And I assume after a night, this is going to be very it's gonna pick itself up. I remember the DSP stream also felt like this because I was quite in my head, so some of them don't even come out the way I want. But thank you for showing up. Cheers everyone for coming. We'll see you tomorrow when we try something again, and hopefully this will have boiled in and I will actually know what to do. Yeah. Thank you. Cheers everyone for coming.